Hey everybody, this is Mr. Bass. Actually, the second time I've started this video, but I just got a phone call from a kid and had to take it. So, we're going to start off with this. This is section 3-3 for Precalc A. Happens to be February 21st, 2021 right now. What are we going to talk about in this video? We're going to talk about logarithms, how to convert between logs and exponentials. We're going to do logs by hand and on the calculator. We're going to talk about the difference between what a log is and a natural log and why they occur. We're going to look at some transformations of logarithmic equations and some basic applications, specifically why there's logarithmic scales. We'll talk about the Richter scale, decibels, stellar magnitude, and pH scales, which measures the acidity in objects, or nitrogen ion concentration and things. Okay, good deal. So here we go. Again, if you had me in data A, we covered a bunch of this stuff, so hopefully this will be a nice Okay, we're going to start off with this right here. How do I convert a log equation? What exactly is a log equation? Well, a log equation will have a log or a natural log. They're both considered to be workable for logarithms. Natural log is just a special one. It'll be the log of a number, and that's right there, to a specific base, and that's right there, and equals an answer. And how that converts is simply like this: b to the x power equals a. So converting to an exponential equation for a lot of you will make these so much easier to be able to understand when we go through some of this stuff. Good deal. So when I say the log of a base b equals x, that means really what I'm saying is if I take the base, to what power equals that a. Now occasionally we'll have logarithms or natural logs written without any little base down here. You know, normally we have a base of 2 or 3 or 4 or 7 or whatever it is. If it's not written ever, then it's implied to be a certain base. So when I ask what's in the box, if it says log and there's no base written, then it's implied to be base 10. And that's because we're humans and we have 10 total digits sticking out of our hands, and that's how we counted, basically signifying the numbers 0 through 9. And if it's a natural log is a special type of log, and it has a base of e, and e is the number 2.71828, and that comes from exponential equations that have continuous growth or continuous decay. Again, we talked about e quite a bit in data A. Hopefully you remember that. Again, 2.71828. It's the number that this 1 plus 1 over n to the nth power, that's what it approaches when n approaches infinity. So when that ratio right there, that 1 plus 1 over n raised to the nth power, when n gets bigger and bigger and bigger and bigger and bigger, then that approximates 2.71828, and it's irrational. It keeps on going forever and ever and ever. Okay, so now we're going to do a few different logs here. So evaluating this. So what is the log of the 5th root of 10? Well, again, remember there's an implied base 10 right here. And if we want to know what that is, I could rewrite that. So this is an implied base of 10. So it's really saying 10, right, to what power equals the 5th root of 10, which is really the 5th root of 10 is the same as 10 to the 1/5. So 10 to what equals 10 to the 1/5, and that, of course, the answer would be 1/5, because the exponents have to be the same because the bases are the same. Okay, so how about over here? Well, again, there's no base written down here, so we know that's implied base e. So if this is an unknown quantity over here, then we'd rewrite e to the x equals here e to the 5/8, because remember, roots become denominators of exponents. So so e to the 5/8, so x happens to be 5/8. Good deal. Now, this one right here says this. Basically, if I rewrote this, it says 10 to what power equals negative 6.28? Well, 10 to the x, if I do a quick little graph, 10 to the x, it looks like this, right? Super steep going up. And you can see that it never is negative, so this would be no solution, be undefined. It doesn't ever, there's no value for logs. You can go ahead and check that on your calculator, but that could be on the non-calc too, just for you to understand, hey, I know that that doesn't work. Here we go. This one, if I rewrote this one, this would be e to what power equals e, I guess you can say that's an implied 1 there, e to the first, therefore x must equal 1. And that's a really important statement right now, that the natural log of e does equal 1, because those are things that are going to, later on when we're solving these logarithmic equations, they're going to cancel each other out. Natural log undoes an e, or vice versa. Okay? So let's go down to here and we'll solve some of these things, or at least we'll try and solve some of these things. So the log of 14 base x equals 2. So I want to know what x is. So if I rewrote it, it would be x to the second power equals 14. And if I go to solve this equation, you know that I would have to square root both sides, and I would get the plus or minus the square root of 14, right? However, my base, being a square root of 14, you're like, ooh, is that okay? Is that not okay? Do I like that? Do I not like that? But that's what we're looking for. Again, you can check it over here on your handy dandy calculator. Let me show you a couple things on this. Clear. So I'm going to go ahead and it looks pretty good, right? Log. You can see that. Log 14. Good. That gives me a number like that. Well, how about that log of negative 6.28? See, it doesn't like that, right? Under the math key, if I go here, there's a button called log base, and this is on the newer calculators. So you can do that. So let's check. So if I put in the square root of 14 as my base, and then I put up there 14, and I hit enter, look at that. It gives me the number 2, exactly what we said. Should work out, but I can't have that base be a negative number either. Okay, so we're good on that. Over here, this would be 3 to the negative 2 power equals x. Remember, that's the conversion that we talked about right up here in the very beginning. 3 to the negative 2 equals x. Well, 3 to the second is 9. Negative exponent means it goes downstairs. So we know that that power would be 1/9. Is that okay? Down here, we're going to talk about graphing, transformations of graphs. Okay, so what does a negative in front do to it? And think about that, right? And what does like a +3 do in parentheses when we're doing this? And I guess more importantly, do you guys know what the heck a log function looks like in the first place? A log function should look just like that. And that'll continue to grow. It will get higher and higher and higher and higher. It's just going to do it really slow, really slow. And the generic one should go through 1, 0. I think I'm going to say this on the next page too, but it's because this is an inverse of an e to the x. A natural log function is the inverse of an e to the x. And we know that. One of the things is they are reflections over the y equals x line. So if I was going to do this one, I was going to say, hey, what does that thing look like? Well, a negative out in front, usually a negative out in front, like a negative in front of an x squared, would flip it upside down, right? And an x plus 3 should move this thing 3 to the left. Okay, so let's take a quick look at these things and see if on our calculators that's... I guess we'll go there. Sorry, I got a little glare on this thing. Yep, I don't like that light right there. So on this, let's go to y equals. Oh, look at that. Looks like we got one of those logistic modeling problems in there. Clear that out. So I'm going to go natural log of x first, just so you guys can see this. Zoom 6. And look, that's what it looks like. Now granted, again, I want to make sure this does go all the way down. It just doesn't show it because there's not enough pixel density. If I change my window so my x is like -4 for that minimum right now, my graph, you can see it shows it going a little further down there, right? And if I went trace, you can see that, do you see how it's saying, hey, there's nothing on the y's? Nothing on the y's. But watch, I just do this real quick. Let's make my x min 0 and my x max 0.2 right now. Can you see how it does go down a little bit further right now? Again, I can't make it so small that it really shows up forever in this area, but trust me, it does go down there. Okay, so zoom 6 again. Remember that last one was all the way down there at like -5, and this one only shows it to -2, so it does go down there further. So where do I want to go? I want to look at this. So let's try this. So this one's saying that it's a negative natural log of x. So let's take a look, natural log of x, at what this does and see if it actually did what I said it was going to do. Oh, look at that. It does do a reflection over the x-axis, right? Which is different than if I would have done this, insert a negative inside it. Then you can see that's a reflection over the y-axis. So if the negative's on the inside, flips it over the y, or a vertical line. If it's on the outside, flips it over a horizontal line. So let's go back to the one that we actually had. So negative natural log, and we said x plus 3. And I told you I thought that x plus 3 is going to move it 3 to the left. So you can see there's 1, and then 3 to the left, and then flipped over that horizontal line. So blue one, 3 to the left, and then flip-flop. Good deal. So there's going to be stuff on your homework that's going to talk about that. Now let me tweak a couple things here just so you can see it. Let's say that I inserted right here an 8. So a -8 natural log of x plus 3. You can see that that's going to be a big old honking vertical stretch on that thing. So just in terms of that notation, the same thing that you would happen if you put an 8 on the other ones. That's what it does. Okay, here we go. So you think about this one. What do you think this is going to do, and why? Okay, pause the video, sketch it out, whatever it is, so you can see it. Don't hit it on your calculator yet. Okay, so hopefully you're here, and we're doing regular logs. And again, I guess I should have showed you this. Maybe this would help. So let's do a log x, which is a base of 10, and do a natural log of x, which again is a base of e. And if I do that, there's my first one, there's my second one. So again, the blue one's a base of 10, the red one's a base of e, and it makes, I hope it makes sense. Because if it was an exponential, it would be 10 to the x, which would make it really steep, which would be close to the y-axis, which means its log would be closer to the x-axis. Because repeating multiplication by 10, 10, 10, 10, 10 is bigger than repeating multiplication by 2.78, 2.78, 2.78, which is what would get you the red line. Okay, so clear, and let's do it. Math, log base. Base of 4, inside my parentheses, negative x plus 3, outside my parentheses, minus 8, and poof. So, window, y min, let's go negative 15, graph. Why does it look like that, right? Why does it look like that in comparison? So, The first thing I'm going to ask about this is because this one moved to the right, and you're like, wait, according to this plus 3, it should move to the left, shouldn't it? Shouldn't it move to the left? Because I got the reflection of the vertical line. That makes sense. That's at negative, right? I got the -8. That takes that whole thing and shoves it down, right? But why did it move to the right if that's a plus 3? Okay, so here's some algebra stuff that you've got to pay attention to. This is really like this. I'm going to factor a negative out of this, and it will look just like this. Negative log base 4 of x minus 3 minus 8. So when I pull that negative out of here, because I want to get the equation to be that negative right here. So I'm pulling that negative out, and when I pull the negative out of the x, I get an x. When I pull the negative out of a positive 3, I get a negative 3. And now you can see that it actually does move to the right, and then it does that reflection if you want to think about how you're going to graph it. Okay? Okay, so we're getting close. We're getting close. And some stuff. So those are some graphs. You guys can play around with the graphs all you want to understand a little bit better. Okay, so what do we have next? So we have this thing called logarithmic scales. And why do we have logarithmic scales first? So run down here. So when we have numbers that have such a big flipping spread in the size of the measurements that we have in that, we tend to want to convert them to something that's a little bit more comparable. Now you guys know that we use this entire mathematical notation called scientific notation to represent really, really big numbers and really, really small numbers, right? Well, sometimes we want to be able to just convert it for specific things. So one of the things that we would talk about is or you can hear a really loud voice. Now, think library, think out on the tarmac at an airport. Those are two incredibly different sounds that you're going to be at. You could think about just a nice quiet field and maybe hear some of the cicadas and the noise that the cicadas make, or the crickets out in the field. Or you could be a headbanger and go see Guns N' Roses or Kiss live in concert and just blowing the speakers out. So sound intensity is one of them. The difference in the measurements for sound is by over a millionth of W over M squared. Earthquakes, huge difference between a little tremor and a big tremor in the measurements. And because they differ by, billions in terms of their size, stellar magnitude, pH, which is the ion, nitrogen ion concentration in items, because those spread out by so much, we've taken all those big spread out numbers and converted them through a logarithmic scale. And the logarithmic scale basically means that it's based on powers of 10. So, for instance, an earthquake whose Richter scale is a 5, and a Richter scale who is a 7, don't necessarily just differ by 2 in terms of their force. That 2 that they differ by is really based on a power of 10. So we do 10 raised to that difference, that subtraction level difference. So 10 squared is actually 100. So an earthquake that's a 5 and an earthquake that's a 7 really has a force or a magnitude of 100 difference between them. Which means if there was an earthquake of a 4 and an earthquake of an 8, that's actually a difference of 4, right? So that power is 4 on a base of 10, 10 to the 4th power, or 10,000 for the magnitude of that. Okay? So we're going to experiment with a few of those different questions. And the first one we're going to deal with is sound intensity. So sound intensity, there's a little chart, I believe. I think it's in your book. You might want to write this stuff down in your book. Here's some of them right here. Hearing threshold, what humans can hear, dogs are better than that, right? But humans can hear 10 to the negative 12, W over M squareds. Soft whisper at 5 meters, 10 to the negative 11th. City traffic, that's not Richland city traffic, that's like New York city traffic, 10 to the negative 5th. If you're down in the subway, 10 to the negative 2nd. Pain threshold, it starts hurting, 10 to the 0, and a jet at takeoff, 10 to the 3rd. That's why you see all the people, if you've ever flown in a plane, all the people out there actually have stuff on their ears, right, to help save them. Okay, so again, in your book there might be some more of these ones than what are just here, and maybe you remember this from data too. Okay, so we're going to look specifically at subway train. Its intensity is 10 to the negative 2nd. We want to know what it is in terms of decibels, because decibels is what we usually talk about in terms of how to know how loud something is. 50 decibels compared to 70 decibels, 40 compared to 100. Where exactly is that? And how much louder is it in terms of sound intensity? So what I'm going to do is I'm simply going to plug it into this equation. We know that I sub 0 is the hearing threshold, so that's 10 to the negative 12th. So if I want to know the decibels for this, it is going to be equal to 10 times the log of I, which is the intensity for a subway train, 10 to the negative 2 over 10 to the negative 12. Okay, so we're going to go ahead and plug that into our calculator. Handy dandy calculator, and you're going to see clear quit. So I got 10 log and 10 raised to the negative 2 power divided by 10 raised to the negative 12th power, down arrow, close parentheses, and you can see that the decibels for a subway train is 100. Cool. So if you're watching this right now, what I want you to do is I want you to look up and just give me a fun fact. You can earn some extra credit right now. Give me a fun fact. What is the loudest concert, rock concert that has ever been, what in decibels, the loudest rock concert that has ever been held? I believe if you look at a little history of it, they don't allow that anymore because people were losing their hearing and damaging their brain cells and all kinds of stuff. But go ahead, look it up, send it to me in an email, and if you're one of the first few that do that, awesome. We'll get you some extra credit on that. Okay. Good deal. So we're going to finish off with this thing right here, inverses from each other. You guys remember, I'll do a quick little thing, f of x equals 2x plus 3, and f inverse of x equals x minus 3 over 2. But these two functions were inverses of each other because f of g of x, or f inverse of x equals x, and f inverse f of x equals x. Or if I plugged in an 8 into here and I got out my 19, I plugged a 19 into here, I got out an 8, they undid each other. Well, that again is what a log and a exponential do. So if this is a log that's just written like this, that's implied to be base 10. So log of x base 10 and f of x equals 10 to the x are inverses of each other, and I want you to see it on the calculator. There we go. So let's go log of x, remember that's base 10, unless I change the base or something, and 10 raised to the x, and I hit zoom 6, and you can see that those things actually are inverses. Remember, again, this blue does curve all the way down, it just doesn't know when it should put those things on. Okay, let me show you again here, just so you're clear on this. Y equals x, I hit graph. They are reflections of each other. Yay, they are. Look, and then I'll show you even on the table. Let's start the table at 5, and Okay, so when I do this, notice that 10 gives me a 1, right, for the blue one, and here 1 gives me a 10. Okay, let's have them go up by tens. Started at 0 and go up by tens. So 100 gives me a 2, and table setup 2 gives me 100. You can see that they undo each other. And of course, the numbers get way too big on some of these really quickly, right? The exponentials, because they are way too big. But that's what allows us to convert to these other scales. Good deal. Hopefully this was beneficial to you. Stay on top of this. This was section 3-3. Mr. Bell's out. I will talk to you later.